We'll be posting the archived version of the webinar on our website within a business day or two. So just know that the slides and the webinar recording are available. So again, happy to have you here today for the ons and offs of energy recovery ventilation effectiveness. 10 to 15 years ago, ERV systems were considered an emerging technology. There are now over 1,500 ERV systems installed in commercial and institutional buildings in Minnesota. ERVs have the potential to eliminate the majority of the energy used for heating and cooling ventilation air. However, many of these systems fall short of achieving their design effectiveness due to a variety of problems, such as improper design, installation, or operation and maintenance issues. According to a 2010 Minnesota Market Assessment Report, only 48% of systems operate properly immediately after installation, with an overall average efficiency of 42%. The Center for Energy and Environment recently completed the field study that Josh will be talking about in moments, characterizing any energy recovery systems in Minnesota commercial and institutional buildings, and it identified common problems that diminish the effectiveness of ERVs. So here's where I love introducing the presenters. We have an excellent presenter with us today. Josh Quinnell is a senior research engineer here at the Center for Energy and Environment. Dr. Josh Quinnell is a senior research engineer in the Innovation Exchange within the organization and has 8 years of research experience in solar energy, heat and mass transfer, and renewable technology development. Currently, Josh is working on a building energy efficiency projects, including commercial and institutional HVAC duct leakage, condensing boiler efficiency monitoring, optimization of ERVs, of course, and residential garage contaminant transport. Josh is also investigating prospects for showcasing solar energy and renewable energy storage in Minnesota. Prior to CEE, Josh spent time at ZAE Bern in Munich, Germany, researching thermochemical energy storage cycles for solar and district energy applications. Josh obtained his master's degree in 2008 and his PhD in 2012 in mechanical engineering, both from the University of Minnesota. So without further ado, Josh, take it away.
All right. Hi there. Excellent. Thanks, Megan. Okay, I have a ton to share with you today. I'm really excited about that, but a few things that occurred to me that I forgot to include in my presentation, I'm going to get out of the way right now. First of all, I need to acknowledge everybody that helped me with this project. First, I'd like to extend acknowledgement to Mary Sue Lobenstein and Mark Garofano at DER of the CARD program, who made this excellent project possible. And then I also want to extend my thanks to the dozens of people I interacted with throughout this project. Building operators, building owners and representatives, engineers, manufacturers, controls technicians. I worked with a ton of people that really helped me learn about how ERVs are implemented, and I hope a lot of that I have communicated in this presentation and my report. Secondly, I want to mention, for those of you who filled out this survey beforehand, that a lot of you mentioned that you were interested in barriers in the field and savings and performance estimates for these units. And I hope that I touch on both of those things in the presentation, so please look forward to that. And then I guess all I have to say is we did a ton of work in this project. We worked on it for 3 years. There's a lot more than I could present here, so please find additional information in the final report. And as always, I'll be available after the presentation for questions or otherwise by phone and email following today's talk. Okay, so time to get real. I'm going to start off with some background and hopefully get you up to speed if you aren't familiar with energy recovery or the practical aspects of implementing it. I'm going to talk a little bit about the expectations which inform the objectives of this project. Some people are saying energy recovery doesn't work. I'll briefly at a high level go over our methodology to set up a discussion about our results, and then from that I want to, I think, take you through the recommendations that I have and how we can use this information we've learned throughout this project. Okay. A very basic background on energy recovery. Typically in buildings, when we talk about energy recovery systems, we talk about air-to-air exhaust energy recovery. More broadly, energy recovery can be applied in a lot of ways, but in buildings, we're generally talking about using exhaust air to precondition incoming fresh air. Buildings need fresh air to satisfy ventilation requirements, and there are heating and cooling loads imposed by having to heat and cool that air. If we can transfer air from the exhaust streams, we can meet some of that load and reduce the amount of energy we have for heating and cooling ventilation air. This is about a ventilation air. Energy recovery systems don't heat and cool buildings. They treat ventilation air. So we say that energy recovery is subordinate to ventilation flows. We have ventilation flows for very specific reasons, and we should do our best with energy recovery to reduce the energy requirements of those ventilation requirements. This is what ERVs look like in practice. On the left, I have some images from product literature. On the top left, I have a total enthalpy wheel. Under that is a plate heat exchanger. It transfers temperature only. The total enthalpy wheel transfers temperature and moisture. And then the bottom left is a membrane plate heat exchanger which transfers both temperature and moisture. On the right is what these systems look like in the field. So on the top two images on the right are total enthalpy wheels we screen in this project. We have one that's sort of mid-size at about 6-foot diameter, and then one that's about 10-foot diameter on the right. On the bottom right, we have a membrane plate heat exchanger sitting in between the air filters, and then on the bottom right corner, we have a plate heat exchanger. This is what we're talking about when we talk about energy recovery today. Energy recovery performance is mainly defined using two metrics. Usually there's only one metric that enters any discussion, and that is the effectiveness. The effectiveness is a ratio with a maximum value of 1, and it's a ratio between the recovered energy, how much energy this system recovers, compared to the maximum possible energy recovery. And the maximum energy recovery is just a thermodynamic maximum. So in practice, all ERVs will have effectiveness less than 1. In practice, most units today have effectiveness between about 0.6 and 0.8. Effectiveness is a really useful design parameter. It helps us determine which ERVs should be paired with which heating and cooling systems, and maybe how to resize those systems. But by itself, it's not that useful for understanding energy savings. It has to be combined with a lot of other information in order for us to get an accurate picture of the energy, in other words, the BTUs that we're saving by implementing the technology. Another parameter, one that is less often discussed but I like more, is called the recovery energy ratio, the RER. Again, it's another ratio, and on the numerator we have the same quantity. This is the amount of energy the system is recovering from the exhaust and putting back in the supply. The denominator in this case is the energy used for recovery. We often consider ERVs as passive components, and that's mostly true. Wheels, however, take a small amount of energy in the form of a motor that has to spin them. But all energy recovery units, even ones without moving parts, use energy because they put another pressure drop in our airstream, and we have to use fan power to overcome that pressure drop. So there's an energy cost there. And the RER then tells us how much energy we're recovering versus how much we're using. And this is really useful because it aligns the performance of ERVs kind of in the same units as the metrics we use for defining heating and cooling equipment performance, for example, EER or efficiency. And an annualized value of RER gets at kind of the energy savings or the total energy savings potential of our ERV technology. Just want to say here that there's a ton of technical resources about air-to-air exhaust energy recovery systems. ASHRAE, AHRI, they have great information. You can learn more from that documentation than I could possibly convey to you today. So from a technical perspective, it's all out there. I like to talk about energy recovery using this chart here. A couple manufacturers use this chart, and I really like it. It basically shows what an energy recovery system should be doing throughout the whole year in terms of outside air temperature on the horizontal axis, and on the vertical axis is the amount of energy recovery. So energy recovery systems should be on, they should be off, and then sometimes they can modulate in between. So traditionally, energy recovery, I think, comes out of warm climates where they use it for cooling. So let's start there. When it's really hot outside, when the outside air has a higher temperature or greater enthalpy than the inside air, we're going to cool it down using the exhaust air. And in this situation, for high outside air temperatures, we're going to run energy recovery systems to do this. This preconditions the outside air and lowers the load on the cooling coils. So our cooling system sees less peak load, and we save energy by running it less. When we're still in cooling mode, but the temperatures are more mild, typically referred to an economizer period, now our outside air temperatures are actually less than our building temperatures, but we still need cooling. In this case, we should actually shut off energy recovery units. They interfere with our ability to use the outside air with free cooling. If they were running, they'd heat up that air and they'd reduce our ability to economize. So In mild cooling weather, we shut ERVs off to get maximum energy savings. Then at the bottom of the economizer zone, we start transitioning into heating weather, around 45 to 55 degrees depending on the building. At that point, our outside air temperatures are less than our inside air temperatures, and we need to heat our incoming ventilation air. This is where ERVs in Minnesota really start to shine. In these cases, we can transfer heat from the exhaust air into the supply air and actually satisfy most of the ventilation air heating load. In fact, energy recovery is usually so effective that we have to modulate it down so it doesn't overheat the incoming ventilation air. And so that's why this curve increases as we go from 45 or 50 degrees. We have very low amount of energy recovery to a high amount of energy recovery at around 25 degrees. And so as it gets colder and colder, the energy recovery system works harder and harder, and at some point, say 25 degrees, it can no longer handle the ventilation heating load by itself. This is where it now works in conjunction with a heating system. In this case, this is the prime heating season in Minnesota from around -5 to 25 degrees. Energy recovery acts as the first stage. It preconditions the outside air. The heating system brings it up to discharged air temperature. At very cold outside temperatures, at iconic Minnesota temperatures, we run into another problem where energy recovery is too effective. In this case, we're not worried about overheating our supply air, but we're actually worried about overcooling our exhaust air. In this case, we're cooling down our exhaust air so much that we can put it below freezing, and we now have the opportunity to condense out moisture and freeze that moisture. And freezing moisture on ERV wheels and plates tends to block airflow, and we like to avoid it or at the very least control it. And so one way to do that, there are many methods for frost control, is to, again, start limiting energy recovery. If we reduce its effectiveness, we can increase the exhaust temperatures and kind of stay out of that zone. So you can see here that energy recovery actually does a lot. There's like 5 discrete things an energy recovery system has to do throughout the year. So we can imagine there's a lot of sequencing that has to go on to make automation systems do this properly, and then it also has to interact well with heating and cooling systems. So it's fair to say that energy recovery systems, or properly implementing them, is pretty complicated. There's one other note here I want to talk about when we consider the performance of ERVs. The flow rates really matter. In this study, we find that units are usually rated and specified at balanced flows, but in actual operation they're operated at unbalanced flows. What does that mean? Well, balanced flows means that the exhaust and supply flow rates are about the same. Say they're each 1,000 CFM. In practice, though, what we find is usually supply is greater than exhaust. Not all the exhaust air comes back to the ERV. Say we have 1,000 CFM of supply, we only have 900 CFM of exhaust. In this case, we'll actually see a bigger change of temperature or enthalpy in the smaller flow stream, so in the exhaust stream, and a smaller change in the supply stream, and this is sort of common. But the really important takeaway here is the energy savings are ultimately going to be limited by the lower flow rate. If we have 900 CFM coming back instead of 1,000 CFM, we're going to reduce our net energy savings by about 10%. So there's other reasons to know about energy recovery. It's a significant part of energy code now. I think in 2015 we moved to ASHRAE 90.1 2010 and IECC 2012. These both have the same table in them. Basically for Minnesota climate zones 6A and 7A, we need energy recovery in a lot of systems, specifically systems that are mid-sized and bigger, and systems that have outside air fractions of 30% and greater. This is an upgrade in requirements from previous ASHRAE standards. I think from 2007, we only had to implement energy recovery at 70% OA and 5,000 CFM. But if we look at the trend, the 2013 90.1 standard increases the requirements for energy recovery down to systems with 10% OA. So from this, we conclude that they're getting fairly aggressive about energy recovery requirements in code, and that's because, frankly, from a theoretical perspective, they save a lot of energy, and in a practical perspective, they do so very cost effectively, often even lowering first costs. Wow, okay, so I hope that that was enough background so that you can follow the rest of the talk. If not, I apologize in advance, but now I want to shift topics. This is normally where we talk about the objectives of the study. Instead, I'm going to talk about expectations. In this study, we predicated the work on expectations from some field work that showed that maybe ERVs aren't living up to their expectations. Turns out this is a lot easier question to ask than actually understand. And so I find myself throughout this project asking this question quite a bit. what are energy recovery expectations? After I ask that question, I find myself throwing up my hands in the air because I don't know the answer to that question. And I'm going to use the advantage of hindsight here to basically tell you what I've learned over the course of this study, and that is this. There are no consistent energy expectations for energy recovery systems. Now, I know there's a lot of engineers with us today, and they might dispute this. I think we all have some performance expectations in mind when we talk about energy recovery systems. For example, if we follow the ASHRAE and the design literature, we know that we often implement energy recovery to reduce design loads on heating and cooling systems. Consequently, we expect that when properly implemented, energy recovery systems are going to reduce the annual amount of energy we use to condition outside air. But I can say this, again, in hindsight from this study, and based on the expectations that people cite, ERVs, if they are missing their expectations, it is not for performance-related issues. And specifically, it's not for these performance-related issues. And I can say that because with respect to the systems we studied in this study, before we arrived, nobody knew what their performance was. We didn't have any evidence that they were working or not working. People were very unclear about what they were actually doing for those systems. So from that, we know that if they're not meeting expectations, and we can maybe extrapolate this to some of the other work, it's not for performance reasons or directly performance reasons. Okay, well, that doesn't exactly help us understand the problem. So again, I'm going to jump way ahead in the study and rely on my hindsight now to generally describe expectations of ERVs. Our expectations generally are that they work and they're not associated with problems. This, again, doesn't really get us anywhere. I have quotes around problems. I'm using like air quotes when I talk about problems because this is still like a nebulous word. We don't really understand what this means. But what we do know is that based on some evidence from the field, there are more problems associated with systems that have energy recovery systems in them. Specifically, we did a market characterization study several years ago that interviewed different groups of people, owners, engineers, and they also documented notes from various callbacks during the implementation of energy recovery systems. We also ran a public building recommissioning study a while back that had a lot of notes about interactions with energy recovery systems. And we found, as Megan noted in the introduction, that there is a lot of problems associated with these systems. And again, problems in quotes because we still don't quite know what that means. But we were able, from the limited data, to kind of characterize generally these main categories. So pretty consistently across all these groups, they were talking about problems related to controlling the systems. We don't really know what that means, but they're at least consistent. To a lesser extent, there's problems that may occur during the operation of these systems. And then a more varied response with respect to whether these problems may be occurring in their design and installation. So there isn't a lot here to go on, but what this does is it sets the stage really for our study. There are problems associated with ERV systems. Specifically though, what are those problems? Do those problems have implications in terms of energy savings? Do those problems cause ERVs to fail to live up to their performance expectations? Those are the questions that we're really trying to get at in this study. So now I'm going to fly through my methodology as fast as possible. If you've got any complaints about this, please see me afterward. We've got three main objectives in this study. First, we don't really know what energy recovery looks like as implemented in Minnesota. So our first job is to characterize ERVs on commercial institutional buildings in Minnesota. Our second step is to take that information and find out how we can form a representative sample of buildings to study and ERVs to study. And lastly, we want to characterize the performance as we find it in those ERVs. We want to document those findings. We want to try to fix the problems that we find, and then we want to associate savings associated with recommissioning those ERV units. More specifically, our characterization work is based on 3 data sets. I previously mentioned this market characterization study and the public buildings enhanced efficiency program that we ran that has a lot of recommissioning notes. And then we were also able to get a lot of very limited information from rebated ERV installations between 2007 and 2012. And this yielded various amounts of information on 400 ERVs in Minnesota. So if our 1,500 number is correct, on the order of 30% of the 25 to 30% of the ERVs in the state, we were able to get some information on. From that, we want to study representative units. So we got to go out there and screen units to find out units that match what we think are representative specifications of energy recovery as implemented in the states. We have an additional task. We want to find problems, or we want to find units that have problems. We want to find units that aren't living up to the expectations of the people that administer and operate those systems. So after we find the representative units, it's all about going out there and characterizing them as we find them. We initially monitored them for 6 months to get heating, cooling, and swing data. We set up trending from their automation systems. We installed our own logging equipment to get our own measurements. We went out there from time to time to take characterization measurements to get at things that we couldn't get from our long-term monitoring. And then lastly, we identified and corrected issues. After that, we kept all our logging equipment in place, and we measured what we found, tried to draw some general conclusions, and then we tried to make some estimates for what our performance expectations should be for energy recovery systems in Minnesota. So we screened a bunch of units. I think we screened 60 units in 20 to 25 buildings. We encountered a lot of different implementations in RTUs, in dedicated outside air systems, specialty units for laboratories, a lot of cool stuff we were able to find. And again, we focused on the ones that were representative of units in the state and satisfied our expectation, or there was reason to believe they weren't living up to expectations. After that, we went and installed all of our equipment on these systems. So we tended to co-locate our sensors with automation sensors so we could test how well those systems were measuring and using those measurements for control. We left our equipment on site. Using a laptop and a logger and remote access, we were able to acquire data and look at it in real time. From time to time, we went back to visit these sites for specific reasons to measure specific things. We used tracer gas methods for measuring airflow and leakage where necessary. We characterized the outlet distributions, especially with respect to where the controlling sensors were placed. Sometimes this meant spending the winter on roofs, which was, well, an interesting experience and ultimately not successful, but it was a fun time. All right, now let's get into all the wonderful things we learned in this study. So I mentioned this characterization work. We learned a lot of things about how energy recovery is implemented in Minnesota. I guess first of all, we found that in the buildings that we encountered in our data sets, they tended to have more than one ERV. About 2/3 of the buildings had 2 or 3 plus energy recovery units, and about 1/3 only had 1 unit. As far as the type of energy recovery systems, total enthalpy wheels dominate energy recovery in commercial and institutional buildings in the state. 80% of units were total enthalpy wheels. To a lesser extent, we found plate heat exchangers that, again, transfer temperature only, and also to a even lesser extent, membrane heat exchangers transferring moisture and temperature. We know there are other kinds of energy recovery systems out there, heat pipes, runaround loops. We know specific examples of them, but in this data set, there were 0 occurrences, so evidently they're quite rare. In terms of the building types, found that energy recovery is most often to date implemented in institutional buildings, about 70%. About 30% of the implementations are in commercial buildings. From the information we have, we know that it's implemented in commercial buildings that have unusually large outside air requirements. This would be auto shops, casinos, gym, sports facilities, that kind of thing. In terms of the institutional buildings, we found that about half of them were implemented in K-12 schools, about a quarter of them implemented in higher education buildings, and the remaining quarter was spread among a lot of different municipal and state facilities. Let's talk about size. We learned some really interesting things here. So of these units we characterized, there's about 3.6 million CFM of rated capacity. Units range over a huge range of size, 200 CFM to 60,000 CFM. What's really interesting, you can see in this chart here, which is the count of unit by type, wheel, fixed plate, membrane plate, is a function of outside air flow rate. Lower quartile, so the bottom 25% of units less than 3,200 CFM constitute only 5% of the flow. Meanwhile, the upper quartile of units, so 25% of units are greater than 11,000 CFM, they constitute 63% of the total flow. This is an important fact. It suggests that really if we're looking at a portfolio of energy recovery in the state, it's the big units that matter, the units that are over 10,000 CFM. In fact, they're about 10 times more important than the small units on a total flow basis. All right, so from all this characterization data, we picked 9 units that we thought would be good for this study. 7 of them, there was at least concerns that they weren't living up to their expectations. 2 of them served as, I guess, what we would call controls. We had reason to believe that they were well-functioning, properly implemented units. We managed to get 6 different manufacturers. We studied 8 wheels and 1 plate heat exchanger. These were in air handling units, dedicated outside air systems, RTUs. They served air handlers, fan coil units, VAV systems, in one case a constant volume system. And they had design, supply, and exhaust flow rates ranging between about 5,000 and 34,000 CFM. And then all of them but one had an AHRI rated effectiveness. It ranged between 66% and 78%. I will note that this is about 10 to 20% higher than the default in our TRM calculation. So on paper, these units are high performance with respect to some of our default assumptions. TRM is a technical reference manual, so it's where we might go to estimate the savings from energy recovery units. Okay, so I'm going to launch right into our high-level savings summary. We went out and measured performance. We found initially on these 9 units they were saving about $41,000 a year annually in gas and electric energy savings. After we left these sites, they were saving just under $58,000 a year. This represents about $17,000 a year in new savings, or an increase of about 42%. If we look at the savings profile, the vast majority of these savings come from gas, almost 90%. We did find some electric savings, which is about 12%. I will say that this is with respect to essentially a EER10 cooling system, so higher performance cooling systems will see less savings. So this is maybe a little bit optimistic and still consistent with the idea that cooling savings are small and probably not the driving focus for implementing energy recovery in Minnesota. Let's look at some of the individual units. So very, very broadly, we had 3 units that were non-functioning. 33% of the units that we encountered in this study were not recovering energy when we found them. On the other hand, we found 3 units that were suspected of not running or suspected of major problems, and they were working basically fine. We had 1 unit that had very non-specific concerns, and we found that it was working great, in fact. And then our 2 units that we hoped were running great, there was no specific concerns, and they did serve as good examples of well-implemented ERVs. They were highly functional and optimized units. After we left, we were lucky in that we had 9 functional energy recovery units. All of our savings, or like 86% of our savings, came from fixing 2 units. 2 of these initial units that were non-functional were relatively large, and by getting them basically functional, we recovered most of our savings. That means that on the 5 units that we implemented the other savings, we only recovered 14% of our net savings, so a few $1,000s. In other words, getting units from not working to working was very cost effective. Fixing a bunch of minor issues on basically functional units was not cost effective. And then we did not find any savings on our 2 units that we hoped were working great. All right, so what did we find? Well, we documented 75 issues on these 9 units over 2 full seasons. And fortunately for us, we can categorize these issues in some very easy groups, and they split up very evenly between the 3. About 33% of the issues we found had clear energy efficiency consequences. The energy recovery was reduced because of these problems, and there was that was associated with real energy losses and real cost penalties. About another third of the issues we call minor issues. This is things that appear in every study. This is dirty air filters, improperly lubricated shafts, this kind of thing. These are real issues. They may have some indirect energy or reliability issues, but there's no strong relationship between these problems and energy performance. And then lastly, we had these other issues that we call performance and expectation issues. Most often these issues do not have any direct energy penalties, but they're really important. These are the kinds of issues that frustrate staff. These are the kinds of issues that, for example, alarms come up on automation systems for no reason. Automation systems don't reflect what's actually happening in the field. There are no direct energy implications, but indirectly these frustrate people, all sorts of people who have to interact with these systems, and then they may, by themselves, mask other issues that we don't notice because staff are frustrated and encountering what we call issues that affect the perception. We did a lot of different categorizations. You can find more in our final report, but I want to briefly touch on this one. We put everything into these main categories, 11 main categories, to try to describe the kinds of issues we found. So most commonly we found issues with control sequences. This is incomplete control sequences. This is missing control sequences, for example, no cooling mode. We found neglected maintenance. Again, returning to our fouled air filters. These don't have direct energy penalties, but according to best practices, we should be regularly changing our air filters. We found installation issues. Often these were associated with energy penalties. Sometimes they were gross negligence on installation. For example, wires crossed on supply and exhaust VFDs, improper staging between heating and heating valves and energy recovery wheels. We found communication issues. These issues were very frequently cited by staff for negative perceptions of energy recovery systems. Again, this is the automation systems that don't reflect what's happening, the automation systems that don't communicate properly what is actually occurring during the energy recovery process. We have issues associated with sensors. So sensors fail, sensors have large bias errors, and sometimes they're just unreliable. We encountered part failures, failed VFDs, failed damper actuators. One particularly pernicious problem we found we call operator overrides. I skipped set points. So often we're encountering conservative set points, especially with respect to economizer and frost control, and there's some energy penalties here. The next category is operator override. These are interesting issues. They can manifest in control point changes like set point changes or actual physical changes, but these we have categorized because through conversations and some assumptions, we assume their basic point was to override energy recovery or disable it. And in most cases, those had severe effects on total energy recovery ability. Lastly, or not lastly, but we encounter design issues too. So sometimes engineers are constrained by, especially in retrofit opportunities, on the choices they make that reduce energy recovery. We found most of these systems operated off design. Their as-operated flows were very different from their design flows. And then lastly, we did come up with some scheduling problems. So we have a ton of problems in a bunch of different categories. That is what is causing energy recovery to miss expectations. But let's look specifically at the energy efficiency issues. We found about 24 issues that we thought were important for analyzing for their energy penalties and cost penalties. And this is the bottom line. If we sum up all those issues we found $23,000 of heating cost penalties per year and almost $2,700 of cooling cost penalties. If you're paying attention, you note that previously I said that we saved $17,000 in new savings, and that's about 50% less than I'm telling you now was there in the sum of the individual issues. It's important to know that many of these sites had multiple issues affecting energy recovery though, and if we fix them all, we can only really claim that savings once. So from that perspective, I think we did a fair job in finding all the savings that could be had. What do those issues look like? So here are a bunch of issues. This is not a complete list, but just some a variety of the things that we encountered. Stuck mixed air damper. We had a lot of operator overrides with respect to exhaust air temperature limits, mixed air temperature lower limits. We had some dampers wired backwards, some incomplete sequences, torn vibration damper, all sorts of things. Exhaust air temperature sensor located right at the purge, miswired wheel and speed control, conservative discharge air temperature set point, failed VFD. These issues range in penalty and cost from a few hundred therms or dollars to a few thousand therms or dollars per year. So these are real costs, and these directly detract from the sole purpose of energy recovery, which is to save energy for energy efficiency reasons. All right, I'm going to change tracks here to talk about performance. So we left all these ERVs functioning and with more savings, and now we think they're pretty representative of how ERVs should be performing in Minnesota. So let's maybe use this subset of ERVs to set some performance expectations. This is a plot I'm using for that. Again, it's recovery as a function of outside air temperature. In this case, it's a cumulative recovery for each of these units, and the shaded region represents all 9 units as we left them in the field. So at the coldest temperatures, they've recovered 0 energy, and as we sweep through the entire year, they've all reached their full potential. Couple takeaways. 60 to 80% of energy recovery for these systems occurs between 0 and 45 degrees. So if we know that energy recovery systems are operating in cold to mildly cold temperatures, we're doing most of the recovery we're going to get in Minnesota. On the other side of that is less than 10% of a recovery occurs below 5 Fahrenheit or above 85 Fahrenheit. We get these extremes in the state, but not frequently enough to really drive energy savings. And again, there's this midpoint between 45 and 65. We have mild energy savings here, either because the ERVs are off for economizer or because the loads are just quite small. Let's look at some other ways that we can describe the performance in terms of the ventilation load. So heating, so ERVs reduce the ventilation load for heating and cooling supply air. We look at red first. This is the percentage of ventilation air reduction for each of the units in this study. We found between about 30% and 90% reduction in the ventilation load. So these are amazing numbers, frankly, but they're pretty in line with the claims on energy recovery systems. We can reduce the majority of heating energy for treating ventilation air through the application of energy recovery. If we look at cooling in blue, we see our ventilation reductions are much smaller. They're between about 10 and 25%. It's a lot smaller because the loads are a lot smaller and because a lot of our cooling load is met through economizer operation. So really the opportunity on the cooling side is at the peak load. That's where the loads are large and we can get maybe 20 to 40% reduction in peak load, which if leveraged allows us to downsize cooling equipment, and that's really the benefit in Minnesota. So heating savings and peak cooling reduction. That's why we implement energy recovery in Minnesota. All right, so I've got this mix of recommendations and conclusions. I want to really hammer on how we should use this information when we think about energy recovery in Minnesota, because a lot of the literature is frankly focused on more mild climates and gives a lot more attention to cooling and not the practical issues, especially as we find them. First thing I want to say is if there were performance expectations, if we were measuring performance with respect to design conditions, most ERVs in this study would not meet them. Units are specified at full capacity and balanced flows, but in practice, exhaust flows are less than supply flows. We have toilet exhausts. We have kitchen exhausts. We're not sending all our exhaust air back to our ERVs. In this situation, performance actually increases. We're boosting the effectiveness on these units because they're excuse the word, effectively oversized, but energy recovery decreases because it's limited by those lower flows. So as operated flows also are just different, let alone on balance, they're different and usually less than design flows, on average about 30% in this study. And this sort of makes sense. Fixed capacity ERVs are installed in variable capacity systems. ERVs in mixed air units only see a fraction of the typical capacity. And then lastly, a lot of the units in the study were retrofit units, and retrofits caused system-wide airflow and building pressure changes that will affect supply and exhaust airflow rates. I wanted to touch on basically very general overview of what we see as the barriers to ERV performance. And frankly, it's just a lack of familiarity among the staff that touch these systems. So what we found in this study is that technicians and operators, rightly or wrongly, they've learned from their experience. They're doing their jobs, but they're often learning from systems that are poorly implemented or implemented in an odd way. And so that informs their expectations, and their expectations are then no longer aligned with what they probably should be if we're out there to guarantee maximum ERV performance. So this is a major barrier. Another major barrier is that there's no real continuous feedback from a staff perspective that ERVs are working. And I'll note here that blinking automation system graphics don't count. They're not necessarily reliable, and they don't really communicate to the operators and technicians what's actually happening. The other part of this is that while we could use energy recovery systems to downsize traditional equipment, in studies, in the systems that we studied, that isn't the case. So when ERVs aren't working, HVAC systems are picking up the slack. ERVs are energy efficiency technologies existing in the background. When they don't work right, the only consequence is more energy for heating and cooling. And this persists, especially if it exists from day one. There's no baseline to compare to. And again, I maybe didn't mention this, but it's actually quite hard to measure and validate ERV performance. There's a lot of nuances to it, and rarely are these systems outfitted with the measurements necessary to do that. So consequently, when there are problems, they tend to persist. And when they are from systems that have informed staff, those behaviors persist. and these problems become normalized and exist for long periods of time. I've got some great news though. I know that maybe seemed kind of like a downer. It's actually very easy to validate energy recovery. So first of all, I'll just say there's no reason to doubt AHRI rated effectiveness. We need to, and maybe this is my impression of this, but we need to stop wasting effort trying to validate effectiveness. We don't care about the effectiveness of heating and cooling coils because we take it for granted. What we do when we implement heating and cooling systems, we make sure those coils are implemented and installed and designed as part of a broader system that performs a goal. And that's really what energy recovery is about. It's not about a specific heat exchanger we're putting in an air handler. It's about all the sequences and sensors and installations that we use to make energy recovery happen. And validating an energy recovery doesn't require a recommissioning effort. ERVs that are on or off at the right times are working. That's it. Okay, there's one important caveat, and that's that we know the flows through that unit, but that's not really an energy recovery problem. That's a ventilation problem, which we're meeting ventilation loads for indoor air quality concerns, maybe some building pressure requirements. Again, ERVs are operating on those ventilation flows, so as long as we have those characterized and our ERVs are on and off at the right time, they're probably doing their job. So the bottom line is energy penalties can be avoided by validating ERVs if staff can identify when an ERV should be running and then assess whether an ERV is running. And so the deliverables we've produced in this project, in addition to our final report, are designed to do this. So we have a quick 10-page guide that tries to get everybody, non-technical audience, up to speed with energy recovery as practically implemented. Just some basic background, a lot of which I've shared with you today. There's a companion guide, which is 4 pages. Its idea is that we can read how to determine the ways in which an energy recovery system is controlled, how we can verify that that's actually happening in the field, and then encouraging operators or someone to go out and do that a few times a year. The idea being, if they can do this, they can make this curve that I talked about early on, which basically just shows when energy recovery is on, when it's off, and we can compare that to some of the things we've learned. If energy recovery system's working between 0 and 45 degrees, it's probably doing most of its job. And we would have to be really motivated to find, to go after savings that are outside of that. So we'd be essentially really concerned about energy efficiency if we want to go from 80% to 100%. And we have that opportunity, and we will characterize it as long as we fundamentally understand when our system's on and off. So I want to give some general commissioning guidelines too. First of all, large energy recovery systems have to be fully recommissioned. We showed early on that all the flow moves through these systems. If we're considering energy savings from energy recovery in the state of Minnesota, we've got to go after the big units. I'll say right now that there were clearly units in our study that were big that were not commissioned, and about 50% to 55% of the issues that we found would have been discovered and fixed in a commissioning process. We have to put some additional burden on the commissioning agents too. We've got to validate as operated flows against design flows. They're different, they're going to change, and we have to know what they are if we want to understand our energy savings. Control sequences should follow manufacturer recommendations, and deviations should be justified by project engineers. The manufacturers really know what they're doing. You can tell from their product literature, the manufacturers I talk to, they've got a handle on how their system should be working, and if we're going to deviate from that, it has to be a justification that everybody can later reference. The control intent has to be established as well as the detailed sequences. They should be specified, and if they have to change, the as implemented sequences should be checked against our design intent and then verified by a commissioning agent or accountable party. And then lastly, there's got to be this knowledge transfer, and a big part of that is commissioning agents giving expectations to operators and building owners about what their energy recovery systems should be doing. These energy recovery systems should be on during specific times, off during specific times. There should be some basic way for us to assess whether they're on or off, and that's how we're going to guarantee savings. Some targeted recommendations. Design engineers would really help a lot if they provided very rigorous specifications, especially with respect to control of ERVs. I'm talking detailed sequences. This reduces a lot of the uncertainty that will happen down the chain. This goes directly into the mechanical and controls contractors. Should be following these specifications. And when they don't exist, they should go back to the engineers and hold them accountable for complete specifications. It's not a mechanical or controls contractor's job to be making engineering decisions in the field. And I know from this project that they're often pressured to do so. But that's an easy way for as implemented energy recovery to deviate from design intent. Commissioning agents, excuse me. Again, ensuring knowledge transfer on system intent, including control. Validate the sequencing, documenting the as operating conditions compared to design conditions, communicating expectations to building owners and representatives. And then lastly, building owners. They got to provide the resources to staff to understand these systems. It's unfair to make operators learn from the systems as they work on them. They should have some idea of an expectation before they administer these systems. And owners should really establish expectations of at least semi-annual operational checks on ERV systems. Again, they're easy to validate, and it's easy to find all the ones that are working. And if we do that, we can focus our attention on the ones that aren't working. Some very high-level conclusions here. ERVs meet their AHRI-rated performance. We had no problem, well, the difficult measurements often impeded our ability to say this, but ultimately we were able to prove AHRI-rated performance on all these units. They offer 30 to 90% reduction in ventilation heating load in Minnesota. They reduce peak cooling load by 20 to 40%. This enables equipment downsizing. This may save demand charges. So it's not the energy recovery component that is the problem. Energy recovery is typically hindered by the practical issues that occur during the installation and operation of these systems. It's a system problem. Non-functional ERVs go unnoticed because they're technologies that exist in the background. The problems go unnoticed because staff aren't familiar with ERV systems and they learn from these systems. So often they're learning from broken systems. ERVs don't meet expectations due to 75 different issues. These are only about a third of the time strong performance-related issues, but the rest of the time they contribute to frustration and negative perceptions of ERVs. And this is the kinds of things that we hear when we ask about these systems. These are the kinds of things that make people less likely to implement in the future. Identifying and resolving specific ERV issues may be time intensive and may be cost ineffective to find the smaller issues, but validating a working ERV is easy. We can find the big ERVs that aren't performing easily and fix them, and we'll get the most of our savings. And lastly, again, I've said this a number of times, but a lot of these issues will be avoided right at the start by commissioning these units and training staff to operate them. That's all I have for my talk. I hope there's time left. If there is, let's take questions.
Thank you, Josh. Could everyone feel his momentum? It was palpable. All right, yeah, we definitely have some questions from the audience. We'll just dive in right away. So have you looked at or analyzed against variable refrigerant flows systems regarding heat recovery? Kind of looking for a comparison, I think, is what the question from the audience is looking for.
No, I haven't. Our treatment of energy recovery was basically designed around those systems that are implemented in Minnesota. And so it was strongly trying to figure out what's wrong with enthalpy wheels and to a lesser extent plate heat exchangers in Minnesota. We recognize that there's a lot of other recovery technologies out there, but we have neglected them in this study.
So an audience member is asserting, so essentially what you're saying is that a third of ERVs in the field basically aren't working. And so how did you consider a control for selection bias in the study, was the question.
That's an excellent question, and it's one we struggled with because we wanted to find ERVs that aren't meeting expectations. Our method for, I guess, not finding all the broken ERVs is that we left that quite vague. So in all these buildings that we screened, we talked to staff, and we understood the reasons they thought they were not working, and we made sure that there was some motivation for us to study the ERV. I guess with the exception of the 2 units that we suspected of working right. So we would expect that from this there probably is some implicit bias that we found 33% of units are not working. That said, I think so that's maybe the worst case. From the prior work though, we do recognize that around 50% of ERVs right from the get-go have reported problems, and that's not too different from what we found. So we found 3 really bad units. We found 3 units, though, that had issues. They just turned out to not be important issues. So I tried to get at this in the talk, but part of the issue is we don't quite know what people's expectations are, and we don't know whether those expectations are aligned with the actual performance or just with the frustration of having to deal with these systems. And so to that extent, I feel we saw both sides of the coin. We saw issues where we've followed expectations that did really result in major performance penalties, but we also saw that a lot of them don't. And it's difficult for us to extrapolate that statewide, but it is easy to say that there's a lot of savings if these big units aren't working, and we should focus on the small number of big units.
Yeah. I think this maybe is specific to a certain slide, slide 27, which is fairly early on, but were you, in that particular slide, we can flip to it, but were you describing the population of units in Minnesota, or really kind of a subset, a smaller sample or discrete sample within the state? Well,
yeah, let's go back to that slide.
Yeah. Yes. Yeah, that was it.
Oh, okay. Yeah, so this is, the answer is complicated. So we did get some information on 404 ERVs. We didn't get all of the characteristics on all the ERVs. So in our report, the answer to your question is that it's documented there, but for most of these questions, we had somewhere between 150 and 400 results. And that varied depending on the piece of information I've given you. For the most common thing we had were design flow rates and design effectiveness, and I say we have that on probably around 75% of those 400 ERVs, and on these other ones, this is by recollection, but somewhere between 150 and 300 responses for these. So a good number, not as many as we like, but hopefully enough to give us a pretty clear picture of what's out there.
Great. We actually have a lot of questions coming in. This is great. I think we're going to try to answer 1, maybe 2 more, and then what we'll do is we'll post responses to the others that we don't get through on the archive webinar page along with the recording before we close out. So did you see any ERVs that caused humidity issues?
No. There's a lot to say about energy recovery and humidity in Minnesota. I didn't really get into that here. No, but a properly working ERV shouldn't be causing humidity issues. We looked at a very small number of buildings, and that certainly wasn't the case. Yeah, I guess I can't really speak to that without getting into a lot more. I guess I'd encourage whoever asked that question to beat me offline, and we can talk about what we learned about that.
Great. Last one. Can you talk a little bit more about the balanced outdoor air supply exhaust with positive building pressurization? This doesn't seem feasible. Is code forcing purchase of equipment that isn't gaining the intended efficiency is the question.
Yeah, that's an incredibly insightful observation. You're right. We basically can't have perfectly balanced ERV systems unless we do some very roundabout design things like routing all our toilet and kitchen exhausts through ERVs, which does also introduce a lot of challenges and may not, in fact, meet code. So essentially what we need to do is recognize that we do not have balanced flows through these units. There's a lot of ways we can incorporate how we typically design ERVs or implement them and estimate savings based on knowing they're not going to be balanced. It's a slide that I didn't have time to share here, but basically just assuming not the design flow rate, but the smaller of the 2 flow rates in your system will give you a much better understanding of energy savings. So that's one thing we could do when we know we're passing back 10 to 20% less exhaust air. If we just use that flow rate number for estimating savings, we're going to get much closer to the mark than using our design flows.
Great. Like I said, we'll try to answer the rest of the questions sort of offline, if you will. And in our last minute, Mary Sue, I'm going to turn it over to you to do some closeout.
Thanks, Josh, for that great presentation. Thanks for attending, everyone. I'm not going to go into a lot of details, but there is, as part of this slide set, which will also be posted, the link to our CARD Applied Research and Development page, which has lots of resources. And then on this slide also are the links to the 3 deliverables Josh mentioned, the final report, the validation guide, and the operations guide. So thanks again for attending, and Megan can go to, yes, great. I just want to mention 3 upcoming webinars that we're going to be doing. One is on July 12th on Small Embedded Data Center Program Pilot, which is also by the Center for Energy and Environment and the Wisconsin Energy Conservation Corp together. Then on July 6th, Illum Advising will be conducting a webinar on the statewide commercial behavior segmentation and potential study. And on August 17th, the White Group will conduct a webinar on a pilot program which investigated an option for expanding utility new construction design assistance programs statewide. And if you have any questions or feedback about either this webinar, upcoming webinars, or the CARD program, please feel free to contact me. My information's on this slide. Thanks.
Thank you, Mary Sue. And as a final closing thought here, I want to point to where you can find the archived webinar recording and slides and answers to the questions that we will answer after we close out. But you can look under resources on our homepage and find reports and materials. And under reports and materials, you'll be able to filter by various types of mediums that we have, reports, webinars, things like that. And you will find this webinar posted there shortly. Lastly, if you are interested in staying up to date on future events and webinars and research that we are doing, I encourage you to sign up for our newsletter, which you can find at the bottom of any of our web pages. And with that, we thank you again for joining us today.